And you guys mentioned that the radio frequency of 100 megahertz or less is the best suitable frequency for observing the planetary transit.
Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system.
Welcome, Soumitra.
Thank you. Thank you again for inviting me in this podcast.
Anytime. Have you guys some snow up there in Massachusetts?
Yeah, it's a little bit. Today it's sunny, quiet, but only 2 days before it's snowing.
Nice. You've well, we're honored to have you on here, and wanted to dive right into more of your exciting research and kind of what inspired you toward this exoplanet and electromagnetism work.
So we thought maybe if we can observe the exoplanet in radio or X-ray or UV, then maybe it can give us some better understanding about that atmosphere. So and that actually inspired us to do this study. So here we mostly focuses on the radio observation to figure out that can we measure the magnetic field of the exoplanet. If we can measure that, the magnetic field, it will give us an idea that whether this planet can retain their atmosphere or not. Because if there is very weak magnetic field or the almost no magnetic field, then you can expect that stellar wind will destroy the planetary atmosphere. So that's why the magnetic field is important. And in this study, actually, we aim to figure out the method for measuring this magnetic field.
Yeah. I was wondering more about the Magnetohydrodynamic MHT simulations you guys used. Looked like this model helped you predict the radio transit modulation between the stellar wind and the exoplanet magnetic field.
Yes. So actually, we solved the MHT equations with the stellar magnetogram of HD. I think it's 128793. I forgot. So HD 128793 star. So I used their magnetogram to model the stellar wind. And then we place a planet as a boundary condition. So we place the planet at certain distance, and basically we change the boundary condition in a way such that the planet will be there, and then we perform these simulations. So basically you can see that we perform the stellar wind simulation, and then we put a planet to study the interaction of stellar wind with the planetary atmosphere. And mathematically, you can say that we use the planet as a boundary condition.
Awesome.
And
wondering also about the alpha and the wave solar atmosphere model. The awesome, I think.
okay, so you see that if you solve the basic MHT equations, there are 4 equations. One is the density evolution equation, basically the mass continuity equation, and another is the Navier-Stokes equation, magnetic induction equation, and the energy equation. So if you solve these four equations with proper initial and boundary conditions, and basically the initial condition will be the magnetogram structure of the star that will give you the stellar wind structure. But problem is, if you solve just only these four equations, it will give you a wind structure with high velocity at the pole and slow velocity near the equator. Basically, if you have a dipolar magnetic field initial structure, so magnetic field are mostly closed near the equator and it's open near the pole. So what will happen that the solar or stellar wind speed will be higher at the open field regime and it will be less in the closed field regime. And anyway, you can say that no magnetic field is actually closed, but if you consider a frame of appearance, then some field lines are open in particularly that frame and some field lines are closed. And in this open field line, wind speed will be higher. So in case of sun, what we have seen that although only the MHT models, which are basically the temperature-driven wind, you will not be explained to this fast wind that observed slow wind structure. In a temperature-driven wind model, you can go up to 300 km per second or 400 km per second, but we don't have observations for other stars, but we have observations for the sun. And for the sun, what we know that it goes up to 800 to 900 km per second. So now point is that how can we explain this speed? Because for the sun, we know that surface temperature is 10 to the power 6 Kelvin around. So we cannot increase the temperature arbitrarily as we have good observation. And with that temperature, we actually cannot explain the observed fast wind structure. And then it is believed that maybe this only the temperature is not sufficient to explain the observed fast wind. And then people started suggesting that there must be some other mechanism which provides the additional energy to explain that fast wind. And this is basically the Alfvén wave, because you know that sun's atmosphere is magnetic and there are many field line loops, and because of this magnetic field perturbation, it will generate the Alfvén wave. And this Alfvén wave actually can generate the additional energy to explain the observed fast and slow wind profile. But again, I am saying that this Alfvén wave model is highly suitable for the solar case. And in that model, what we did, you have to solve the two additional equations for Alfvén wave, because Alfvén wave can propagate along the field line and opposite to the field line. And these two Alfvén wave, one will be the propagating Alfvén wave outside, and when it will propagate outside, some part of this Alfvén wave will be reflected because of the density inhomogeneity. And now this outward Alfvén wave and the inward Alfvén wave will collide and will generate the turbulence. And this Alfvén wave turbulence will give you the supply of that additional energy. So basically you have to solve all the four MHT equations plus two additional Alfvén wave equations, one for propagating Alfvén wave, outward propagating Alfvén wave, and another is for counter propagating, means reflected Alfvén wave. And these two, if you solve these additional two equations, it will give you the turbulence energy amount, and that actually is necessary to explain the observed fast wave in the sun. Again, I am saying that this is more suitable for sun because we don't have observations for other stars. Means if the star is very massive, means high mass star, one can expect that the wind will be mostly temperature driven. But for solar-like mass, this Alfvén wave-driven model is the most suitable because only temperature will not be able to explain the observed structure.
And then on top of the Alfvén waves, it looks like that the star-planet interactions in the radio and ultraviolet and X-ray might also help
Yes,
explain more about the magnetic field of the planet.
magnetic field of the planet. So what we found there, that actually we placed the planet at different distance from the star, and we also changed the planetary orbital distance, as well as we studied at different frequency, radio frequencies. And what we find that and in our model, what we did new here, that for the first time we implemented the planet moving around the planet self-consistently. Because most of the previous studies, they are only able to do this study by placing the planet at one specific position. But in our simulation, it is time dependent. Means planet is exactly moving around the star in a orbit. And that development actually allows us to do the study of transit. So as our planet is now moving around the orbit self-consistently, it actually captures the influence of planetary motion on the surrounding atmosphere. And most of the previous study actually missed this because they are not able to capture this time-dependent motion. And when we are able to do this, and then we perform this study by placing the planet at different distance, and we found that the radio behavior of the radio transit very significantly, means radio signals modulates significantly. So now if we can observe these radio modulations, then actually it will give us an idea about the exoplanet magnetic field. And here we have clearly shown that this exoplanet magnetic field, this radio modulation is highly correlated with the exoplanet magnetic field. And that way, but we also did the same study for Xray and UV, but unfortunately we don't find any significant modulation in case of Xray and UV. But point is that what magnetogram we use to model the stellar wind, that is not very good because there is no such good observation of the stellar magnetic field. So it's very low resolution magnetogram image we use to drive the model. So that may be one of the causes that we don't find any kind of significant modulation in X-ray and UV. But for radio, we found quite significant modulation. And specifically,
yeah, it's and so you guys primarily focused on the radio waves, not the ultraviolet and X-ray spectrum.
Right? No, there is also one section in this paper about the X-ray and UV.
Okay.
But we don't find any significant change in case of X-ray and UV.
Why is that?
Yes, what I told earlier, that we exactly don't know, but it is probably due to the fact that the magnetogram we use to drive the stellar wind is very low resolution. As we said that we don't have good observations about stellar magnetic field. So as it is very low resolution, and also second point is that in our model, we don't have any kind of flare or semi. So if flare and semi happens, then much higher amount of X-ray or UV emission will be generated. And then only we can actually, if the star did not produce significant amount of radiation in X-ray or UV, then you cannot expect modulation much. Because what will happen that when the planet orbits around the star, some of the radiation will be blocked by the star, blocked by that planet, sorry. And then one can expect a drop actually, when it will be at the mid-transit point. But if the star itself don't produce much X-ray and UV, you cannot expect that. So sufficient amount of X-ray and UV emission production is necessary. But probably this is our model problem of selecting the stellar magnetogram, maybe for other star or where there is a good observation is necessary, you can get something different. But for that star, it's very unlikely.
Yeah. I'm curious on like as the planets in transit in front of the star, in the mentioned for a very short period of time, only to 4 to 5 hours, depending on the period, how that modulation is compared over that planet radio transit.
Okay, point is that let's say you have star and the planet is moving around the star. And your telescope is here, it's in the line of sight. Now, when planet is far, then you can expect almost most of the radio emission will directly come into your telescope. But now, when the planet will come here, just along the line of sight, so what will happen? The planet will block some of the radio emission wave coming from the star. So what will happen? You can expect a drop at the mid-transit, and obviously if your telescope is located at this point, so you can expect a drop. But problem with radio emission is that during the propagation of radio wave from star to the telescope, it suffers significant amount of refraction. While in case generally people do the optical observation till now, and advantage of optical observation is that for optical emission does not suffer much refraction. So in case of optical, what the Kepler's mission is doing in the optical observation, so in case of optical, what you will find that there will be when the planet will be along the line of sight, it will block the emission and there will be a drop. And from that drop, you can detect the exoplanet. So, but in case of radio emission or radio X-ray or UV also, one can expect this kind of drop. But in case of radio, what will happen? Extra that as it suffers significant refraction during its propagation, so sometimes you can expect an increase also. Specifically when the planet will be very close to the line of sight and this magnetic tail of the planetary magnetosphere will focus some of the radio wave into the telescope. And that is the reason that radio emission will be highly modulated. And somehow what we find that this focusing or the blocking of the radio emissions actually depends on the structure of the planetary magnetosphere. And we know that planetary magnetosphere again depends on the planet's magnetic field.
Yeah, and we were wondering with the transit method, how could we be sure that we're not overestimating the radius of the planet,
We are not,
considering if even if we're imaging with telescopes and the optical,
yes.
the magnetosphere is what, like 2 to 3 Earth radii out, something like that.
Hmm.
And so we're wondering if some of the exoplanets are overestimated in size.
Yes. In case of optical, it is very difficult to say. Because in case of optical observation, generally they don't focus much on the exoplanet magnetosphere structure. They only focus on the detection. Means if you can find a drop, so there must be a planet. Then,
Like in terms of the infrared and the UV, right? Wouldn't that potentially, there would still be some absorption and deflection with the magnetic field in optical?
yes, there will be some, but generally people focus only on the blocking part.
Yeah.
They generally don't focus on the magnetosphere part, means how much will be the planet area or size. It is actually difficult to say from the Kepler mission, from the optical observation. But recently they sent another mission which is TESS. And TESS mission is supposed to give some idea about the size. But that is also very unlikely. Because how much drop, I mean, you can say that if your magnetosphere structure is bigger, then you can expect a higher amount of drop because it will block the much more radiation. And if your magnetosphere size is bigger, that means probably the planet size is bigger, but you cannot say that directly. Because even if you have a planet of lower size, if it has high magnetic field, then planetary magnetosphere size may be bigger. So it is, I don't know, but it's difficult actually to exactly estimate the size of the planet. But you can estimate the size of the magnetosphere structure. But that may give you some idea about the radius, but not exactly. And also, if you can figure out the magnetotail size, or when the solar wind hits the planetary magnetosphere, there is a point where the solar wind pressure and the field pressure from the planetary magnetic field pressure is almost equal. And if you can figure out the specific point, then actually from some mathematics we can estimate something about the size and areas. But problem is that it is very difficult to do.
Yeah, and it seems like the proportional flux along the magnetotail would be proportional to the sum of the reflected ions, or curved or bent, across most of this spectrum.
Yes.
But it might be difficult to differentiate like the ray waves with what's with like between the X-rays, the radio waves, and the UV and the infrared. You know, they all kind of they're meshed together in this magneto-tail flux. You know?
Yes. Yeah, that's the idea. But problem is that first we have to detect. In our model, what we find that even if radio modulates significantly, it is very difficult to detect with the present instrumentation capability. Only recently, I think in 2019 or 20, the instrument called LOFAR, low frequency radio array telescope, which is the basically a ground-based telescope, that actually find some exoplanets. But again, means we need phase-based radio telescope probably, or very high resolution radio telescope to detect this kind of modulation. But if we can detect, means then probably we will be able to figure out this kind of behavior. But detection is a very difficult task.
Yeah,
And what in our model also we found that the radio emission, what the star generates, it's very less. So it's very difficult actually to detect with present instrument.
and also some of the math that you guys did looks like it makes a lot of sense with the ray tracing algorithm to
Yes.
calculate the curved path of the radio waves, and you guys integrated over the ray trajectories or emissivity and calculated the intensity of each pixel. Yes.
Yeah, emission. But point is that in our model, we only generated the thermal radio emission. But till now, no instrument is not actually able to detect the thermal emission. Most of the instruments, ground-based, till now only able to detect the coherent radio emission, basically the radio burst. And radio burst actually only found when there is a flare or CME. And then actually the proton and electron particles will be accreted. And because of that accretion, they will generate some synchrotron radio emission. But in our model, actually, we don't have this particle propagation method that we are aiming to do that in future. So to generate the radio burst, one have to couple this model with the energetic particle propagation model. This is also known as the ACP model. So that one have to couple. And then only we will be able to calculate the synchrotron radio emission. But for now, it is only the thermal radio emission. And thermal radio emission is very difficult to detect. And radio bursts are only possible when there is flare and CME. But that thing, we are planning to do this in future, that what will be the impact of CME on flare on the thermal emission as well as in the non-thermal emission, radio emission.
Seems like some exciting astroplasma physics going on.
Yes.
and so you gotta take a look at these graphs to understand the modulation in the it looks like there was significant modulation in the
Yes, we found almost 50% modulation. So it's significant, really. It's highly significant. The problem is the detection. Its total emission is very less.
And then the 30 megahertz um, showed some promising modulation too. Like, but it really depends on the orbit. It looks like.
Yes, it depends on orbit, but actually what you will see in these two plots, that for a higher frequency, there is always a drop. But for lower frequency, like 10 megahertz, 30 megahertz, or 20 megahertz, behavior is quite defiant. Means it did not drop always. That is because if radio frequency is low, at lower radio frequency, it suffers very high amount of reflection. So, and these reflected waves can come into the radio telescope from any angle. And that actually changes the behavior of the radio transit at lower frequency. But at higher frequency, actually high frequency don't suffer much reflection like low frequency. So in high frequency, you will always find the drop. But at low radio frequency, it will be quite random. Means sometimes it may increase and sometimes it decrease. That is because of the reflection issue. And that's why the X-ray and UV observation is not important. Because in case of X-ray actually don't suffer much reflection. And even if you see these radio astronomical studies nowadays, which is mostly used for the pulsar study, it is from a radio image, it is actually very difficult to determine where the pulsar is exactly. Because when the radio emission comes from pulsar to your telescope, it suffers very high refraction. So maybe your telescope is here, maybe pulsar is here, but radio wave affects so much that it comes from this angle and sometimes it goes out this side. So it did not actually use the telescope. So it is very difficult from that radio observation where is exactly the source, means pulsar, let's say. And in case of exoplanet observation, it's also the quite behavior is similar. But problem is for pulsar, we know that radio observation is only option because pulsar only emits the radio. Pulsar don't emit in optical and X7 much. So as it only emits in radio, so the only way to observe pulsar is in the radio. But for other stuff, we have other options like X-ray, UV, and optical kind of observation. But X-ray observation is much more better because X-ray actually don't suffer refraction. So if you have star and a planet, X-ray can come almost directly. So X-ray can give us the clue, but point is in our study actually we don't find that. Probably it generates very less amount X-ray. That's why.
And you guys mentioned that the radio frequency of 100 megahertz or less is the best suitable frequency for observing the planetary transit in radio.
But at that frequency, actually, we found the most high drop. Means drop is larger at the 100 megahertz frequency range. But if you ask me that why the 100 megahertz, that we again don't know much.
That's
what we
the question. Yeah.
Yes, if you ask that why 100 megahertz will give you the larger drop, that actually we don't know. That why only 100 megahertz, not the higher.
There's got to be some kind of relation to the intensity of the field. And those wave interactions. I'll have to think about it. But I think your study, like these electromagnetic spheres, should really stick out like a sore thumb. Uh, it seems like most of the research they're not really considered in the optical.
Optical? No, most of the studies still now in optical.
Yeah.
But no, most of the studies still now not considered these other bands because of the observational difficulty. Because observation in optical is quite easier, and most of the telescope like Kepler and TESS all are in optical band. But problem in optical band is that it will only help you to detect the exoplanet. But if you say that this planet exists, that's all. But if you want to know about the details of the planet, like how is the structure of the planetary atmosphere, what is the planetary magnetic field, what is the temperature at that planet, then you need other observations. Means optical observations will not help you to do that. And
So
problem is that we now have thousands of observations regarding exoplanet. Means we have discovered lots of exoplanets. So detection part is now quite over. Means we have already detected many. So it's now time to understand the atmosphere of these planets, because this will only tell us that is there any possibility to have a life or not in that planet. Because what I say, only the two conditions. One is temperature 0 to 100, that will tell you that liquid water exists, and another condition is the magnetic field. If you don't have the magnetic field, there will be no atmosphere on that planet. So this is the two most important conditions.
So we're wondering with like what would such a space-based telescope look like? And there's one planned in the radio.
Yeah, there is still now no space-based radio telescope, because radio telescope consists of basically many antennas. So it is till now we have developed only ground-based radio instruments, but in space-based probably we have to send few satellites, and in every satellite there will be some antenna, and then by that. But I think actually I am not an expert in this instrumentation domain, but I think they are planning to send a sunrise mission, which will be a space-based radio observatory in around 2025 or 6. NASA is actually planning to do that, but that will be only focus towards the sun. So, and another possibility is to place the area observatory in moon, in lunar surface. So that is also very difficult, and I think very costly also.
It seems like L2 might be a
So
good spot.
yeah, best option is the ground-based instrument at this moment, and till now LOFAR is very good, but next upcoming radio telescope is the SCA, and SCA-1, SK-1 and SCA-2. Probably SCA-1 and SCA-2 will give us some idea about the exoplanet, because LOFAR already detected few exoplanets, but LOFAR is also till now not able to characterize the atmosphere, which we need more high resolution to exactly figure out what is happening there. And probably SCA-1 can help us, but at least I think SCA-1 will be able to help us in case of radio burst. Basically, when flare or semi will happen, that behavior I think SCA1 will be able to detect, even not the thermal emission.
But I also wanted to, along the lines of space-based imaging, could we potentially, put this on a satellite and face it toward Earth and image in the radio wave spectrum, these modulations?
What other stuff?
Like here on Earth, this approach that you guys have taken, there's got to be so like a lot of other applications here for Earth too.
Yes. Because of sun, actually, we can do this study, but still means for sun also we need a phase-based telescope. Means
Like if we're familiar with synthetic aperture radar and how we might be able to put 30 to 100 megahertz radar antenna, toward Earth, if we could, could we image these electromagnetic fields here on the surface and, maybe from trees or 10 hertz or buildings or who knows?
that may be a possibility.
But it'd be like the radio waves would be reflected if they are, because they're not like bent, so it's tricky.
No, reflection is also there. It's bent and reflection. Means because if you see the expression that the dispersion relation, and it will clearly tell you that if the density is above the critical density, it will be reflected. So even if your telescope is here, some will be dented and some can reflect also. And this is actually highly true for low frequency radio. For higher frequency, it's quite unlikely, but still it may happen. That's why behavior of radio is quite difficult to predict. The behavior of radio emission.
Yeah, it seems like the modulated radio waves could detect the location of an object of interest, that generates or perturbs an electromagnetic field.
Yes.
And it seems like you could almost apply it to on like a micro scale too, and yeah, about a lot of exciting future research. So
yeah, this necessary to study in more detail. Specifically, I am more interested in the non-thermal part. That's what will happen if there is jamming, and if when the particle will propagate, means how will be the behavior of synchrotron emission, and what will be the behavior of X-ray emission at presence of CME and flare. Because in our model, it is surely very less amount of X-ray. That's why you don't find anything. But
there's 1,000 Earth-sized planets within 50 light years out. So
yes,
curious if you guys have future research and plans to help Earth and the system identify how many of these planets have magnetic fields?
Yes, that is actually, I think most of the planets have magnetic field, but few planets actually also don't have. But even if they don't have a magnetic field, they also have an induced magnetosphere, because what we have shown in our study that planet does not have a magnetic field, but then also Taylor can generate an induced magnetosphere on the planet. So, and this observation will give you the magnetospheric structure. But problem is that if you don't have a magnetic field, then Taylor wind actually will destroy. Means you cannot expect life. And another thing is that in our study, we only focused on the closing orbit. Means orbits are very close. Means like you can say in case of solar system, the distances are like Mercury and Venus. You can say it's only, I think, 10 or 20 solar areas.
And
Specifically, people are now looking for JWST mission. Probably JWST will give us some idea about the composition of the exoplanetary atmosphere at least.
yeah.
And from that composition, actually one can estimate the behavior of temperature. Means not much, but still you can expect something.
We'd also be interested in collaborating on research to help quantify how the thickness of the atomic oxygen layer of a planet, how this correlates to the magnetic field intensity that we observe, and because there should be a correlation flux and how that the UV flux relates to the splitting of the oxygen and everything. Yeah.
Yes, I exactly not sure, but
thanks to you guys, we're one step closer to launching these spaceships to exoplanets.
yes.
Well, thanks so much, Soumitra.
Thank you. Thank you
Great
again.
work.
Thank you again.